Hello, and welcome to Chemistry with Dr. Clark. In the video today, what we'd like to talk about is calculations involving the heating and cooling curves. In order to do these calculations, basically there's two formulas. You've got the Q equals mc delta T, and you've got Q equals N delta H bar. That's the line over the top. If you are feeling comfortable with using both of these equations, then you should just stay with us and we'll do some calculations. If you haven't really worked with either equation before, then it's probably a good idea if you go back and take a look at two of my other videos. There's one talking about the specific heat capacity problems. It uses this equation here. It talks about how if you're given all of the variables except one, how would you solve for the missing variable, right? How would you find mass, or how would you find specific heat capacity? The video that goes with this equation is called thermochemical equation problems. And basically, this is the equation we use when we want to do some calculations with thermochemical equations. And again, it talks about how do you find your N, how do you find your delta H bar, how do you calculate your Q. So if you are feeling like you need a little bit of extra help in either one of these, there is help available. You just have to go back and take a look. So if we take a quick breeze through the equations. In this equation here, Q is going to be your heat, M is your mass, C is your specific heat capacity, sometimes known as just specific heat, and delta T is the change in your temperature, the final minus the initial. Now, with these problems, there are a variety of units, right? Your heat can be in joules, or it can be in calories, or kilocalories, or kilojoules. There's quite a few. The main thing is when you're doing these calculations, you want to be consistent, okay? So let's talk about the specific heat capacity. Specific heat capacity is usually measured in joules per gram degrees Celsius. That's the one we tend to like the most. Which means that you've now defined the units for everything else, right? This has grams in it, so when I measure my mass is going to have to be in grams. It has degrees Celsius in it. When I talk about changes in temperature, they're going to have to be in degrees Celsius. Now, neither one of those are really a problem because masses, we like to talk about them in grams. Temperatures, we like to talk about them in degrees Celsius. The only one that really is variable is the heat, right? If we're going to go with this as our specific heat capacity unit, then the heat will have to be measured in joules. But the heat could be measured in kilojoules as long as this is in kilojoules per gram degrees Celsius. Your heat could be measured in calories as long as this is calories per gram degrees Celsius, right? It just has to be consistent within the formula. Now, this calculation here, we like to use this formula when there is a temperature change. Let's say that you've got a glass of water, it's at 25 degrees and it warms up to 35 degrees, right? So there's a temperature change. It's going from 25 to 35. So whenever you have a temperature change and you want to know the amount of heat involved, this is the calculation you go with. This calculation down here, N is going to be your number of moles, and your delta H is going to be your molar enthalpy. Okay, molar enthalpies tend to be listed as kilojoules per mole. That's the way we like to talk about them. Now, it can be calories per mole, it can be joules per mole, right? Again, the unit here is a little variable, but once you've chosen your unit here, you have to be consistent throughout the rest of the formula. So your moles will be measured in moles. And if I've decided to go with kilojoules per mole, then my heat has to be in kilojoules. And similar to above, right? If I decided I wanted to talk about heats in calories, that's okay as long as my molar enthalpy is in calories per mole. Okay, this formula here, we tend to use this one when there is no temperature change. Think about melting ice. If you have an ice cube, the ice cube is at 0 degrees, and when it melts, it turns into water at 0 degrees. So it started at 0, it ends at 0, but there is a change, right? It's going from solid to liquid. So if I want to know the amount of heat that's associated with melting an ice cube, this would be the formula I use. This one here is used when there's no temperature change. This one is used when there is a temperature change. All right, now let's talk about the situation that we're attempting to approach in this video. We want to have something, let's say you have a block of ice. Let's say that you are at the skating rink, you are playing a game of hockey, you're doing some figure skating, some ringette, you're somewhere where there was ice. And so when you come out, there's this chunk of ice stuck to the bottom of your shoe or your skate. Now, at the rink, it's very, very cold. So let's say that this ice is at minus 10 degrees. And through some sort of long and varied story, we'd eventually want to turn this into steam at, say, 120 degrees. Okay, we've accidentally thrown it into a pot. It's been used to cook with. The steam is coming off, and the steam is 120 degrees. So the question I want is, how much energy is needed to get minus 10 degree ice to turn into 120 degree steam? Right? That's quite a bit of a change. And it's a series of small changes. Right? Your ice cube is not going to melt at minus 10 degrees. Ice doesn't melt at minus 10. It melts at 0. So the first thing that you're going to have to do is you're going to heat up this block of ice from minus 10 to 0 degrees. Right? Now there's heat going to be involved here. So you're going to have to put some heat in to warm up that block of ice. Once your block of ice hits 0 degrees, then it'll actually melt. So then it'll turn into water. Now it's still going to be 0 degrees, right? When an ice cube melts, it'll go from 0 degree ice to 0 degree water. But you are changing it, right? You're going from solid to liquid. So you are going to have to put in heat to make that change. Now, if you want to warm up your water, right, because it's 0 degrees, if you're going to put it in a pot and use it to cook something, right, you're going to have to warm that water up. So I'm going to add some heat to that water to warm it all the way up to 100 degrees. Now, once your water is up to 100 degrees, that's the boiling point of water, so it's going to turn into steam. But kind of like when you melted your ice cube. If your ice cube started at 0, it turns into water at 0. When you boil water, it starts at 100 degrees water, and it's going to turn into 100 degrees steam. So there's a heat that goes with that, right? A heat with turning liquid water into steam, both at 100 degrees. Now, in this particular problem, I don't want 100 degree steam, I want 120 degree steam. So again, I'm going to have to put some heat in to make the temperature rise from 100 to 120. So for this particular problem, there's actually 5 different places where I'm going to put heat in. Warming up the ice, melting the ice, warming up the water, boiling the water, and then warming up the steam. So in the end, I'm actually going to have 5 different heat values that I'm going to add together. Now, each particular step is relatively straightforward, right? This is a temperature change. So I'll use my formula that involves temperature change. This change does not involve a temperature change, so I'd use this formula. Warming up the water, temperature change, use the first formula. Taking the water and turning it into steam, no temperature change, so use this formula. And then warming up the steam goes back to the first. So you can see it kind of alternates. This one, then this one, then this one, then this one, then back again. The actual calculations of each individual Q is not difficult. The difficult part here is trying to keep yourself organized because you have a lot of temperatures happening. You've got heating, you've got phase changes. When you turn to a solid to a liquid, that's a phase change. And so the biggest thing with these problems is attempting to organize your data, right? See what you have, see what you're looking for. So let's take a look at an example or two. For these things, the first step that you do is often just drawing the diagram, okay? We're going to organize our information into a heating or a cooling curve. It's a diagram that's just meant to organize our information. So that's what the first one is here. Okay, the first one does not ask you to do any calculations. It just wants you to organize the information into a diagram. So it says, liquefied chlorine gas at minus 40 degrees and standard pressure is cooled to minus 130 degrees. So you're going to start at minus 40 and then you're going to cool it down. I would like to sketch the cooling curve for the chlorine, showing the regions of phase change and temperature change. Chlorine gas melts at, chlorine gas boils at. Now, I find that if you follow the same steps every single time, you get into a pattern for doing these, and you have much less of a chance of making a mistake. Now, for me personally, if I'm going to do a heating and cooling curve, it's going to be the full size of the page, because I need lots of room to be able to put in for my information. So let's draw ourselves a graph. On this graph, your x-axis is going to be your temperature, and your y-axis, depending on which textbook you're looking at, they do label it as different things. Sometimes we'll call this heat, added or removed, or we could call it time, right? Because it does take time for the heat to be added or heat to be removed. So it depends on what your textbook says. Now, if I was going to do this, my very first step is to define the limits of my problem. What is the absolute lowest temperature that I'm worried about? What's the highest temperature that I'm worried about? Okay, let's say that we're talking about a glass of water. If I was only worried about my glass of water going from 25 to 35 degrees, then my entire graph would be between 25 and 35, because that's the only temperatures that I'm worried about, right? I don't care what happens below 25. I don't care what happens above 35, right? If my whole focus is just between 25 and 35, then my entire graph is going to be between 25 and 35. In this particular problem, it's talking about the whole graph being between minus 40 and minus 130, right? Gas starts off at minus 40, it cools down to minus 130. That's my window that I'm looking at. So in this graph, I'm going to put the lowest temperature pretty close to the bottom of the graph. I'm going to put the highest temperature pretty close to the top. So it is going to start at minus 40 degrees Celsius, and it is going to cool down to a minus 130 degrees Celsius. So first step, figure out your highest temperature and your lowest temperature, put them at the top and bottom of your graph. Your second step is going to be putting in melting and boiling points. Okay, so this problem does tell me I have a melting point. It does tell me I have a boiling point. Now, the key here, if your melting and boiling point follows within this region of your graph, you're interested in it. If your melting point or boiling point falls outside of this region, then I don't care about it. Okay, take a look at my boiling point. My boiling point is at minus 34 degrees. Minus 34, if that's minus 40, minus 34 would be up here somewhere. It's not in the region that I'm interested in. So even though I've given the boiling point, even though it does have a boiling point, it's not in the temperature window that I'm concerned with. So my boiling point, I can just ignore it because it's not somewhere where I want to be focused. Now, if you do look at your melting point, though, it has a melting point of minus 101. Minus 101 is somewhere between minus 40 and minus 130. So I will put in the melting point because that is in the window I'm looking at. Now, depending on who's asking you to do this problem, they may require you to draw this as a scale. So if you have a scale, minus 101 would be about, say, here. But for most things, scale is not important here, right? It's just organizing your information. So if you have control over it, personally, I put it right here in the middle. Okay, so I'm going to put in my minus 101.0 degrees Celsius. Now, you know that this is not the scale in the least, right? This is a 60-degree change. This is a 30-degree change. But I have spread it out because eventually when I draw my picture, I want to have space to show things. Okay, so if you don't have to do a scale, then you can just leave it out. Whoops. Okay, now let's talk about what happens. If you are at the melting point, that means you're going to melt. You're going to go from a solid to a liquid. Okay? And if you're going between a solid and a liquid, there's no temperature change. So your temperature is not going up, your temperature is not going down, there's no temperature change. So for this part of the graph, I'm going to have a very nice flat horizontal line. Okay? And this is where I'm going to have melting happen, right? Because if you're melting, no temperature change. So if we then talk about what's actually happening, it says you started at minus 40. You're here. You're going to cool it down, so the temperature is going to change. Well, the temperature just doesn't go kablunk, drop. It takes time, or it takes the removal of heat to make that temperature drop. So it's a gradual thing. So you're going to have a sloped line here. Because as time passes, as heat is removed, your temperature is going to drop. Then you'll hit your melting point. Maybe we should label it. And once you hit your melting point, the whole thing is going to melt, but it's going to stay constant temperature. Now, once that's finished and you start removing more heat, well, then you start going back into cooling, right? It's just going to get colder and colder and colder until eventually you get to your final temperature. So if you've got a melting point, and if our boiling point was part of the graph, then those would be nice horizontal lines. And what connects the horizontal lines? Sloped lines. Now this particular graph is a cooling curve, so the sloped lines are sloping downwards, right? Because you're cooling it down and you're cooling it down. If it had been a heating curve, and I believe the next example is a heating curve, it actually would go up. So you'd heat it up, level it off, heat it up. Okay? Now I really would like to label this thing. So if I'm going to label this, maybe off to the side we should put in a couple of notes here. If you have a boiling point and a melting point, okay? Melting points are always higher temperature than, boiling points are always higher temperatures than melting points. Under your melting point, if it hasn't melted yet, it's a solid. If it's above the melting point, that means it has melted, so it's a liquid. And if you're above the boiling point, that means it has boiled and you are a gas. Okay? This is extremely important. You need to be able to label the parts of your graph as being solid, liquid, or gas and not get them mixed up. Because eventually, when I start pulling numbers from my equations, I'm going to have to use the numbers that go with the solid. So if you've mislabeled the part of the graph that's a solid, then you're going to be pulling in the numbers for the wrong thing. Okay? Now, for this graph here, I don't actually have my boiling point included, so that's kind of gone. But I do have my melting point, right? If you are lower temperature than the melting point, you're a solid. If you're at a temperature higher than the melting point, you're a liquid. Okay, so this part of the graph talks about liquids, this part of the graph talks about solids. And that does kind of go with our problem, right? Because it says you had liquefied chlorine. Well, if it's liquefied, it's a liquid, right? And then you cooled it down. If you're cooling a liquid down, there's a decent chance that eventually it'll turn into a solid. Now, I did talk about this as the melting point, right? But two different things happen at a melting point. If you're putting heat in, the substance will melt. But what about if you have a liquid and you're pulling the heat out? It doesn't melt, it would solidify. So this here would be considered to be solidification, which is the opposite of melting. Now, when we're talking about water, we think of water as melting and freezing. We like to talk about, well, it melted versus it froze. But in the world of chemistry, we don't tend to use the word freezing as the opposite of melting. We like to use the word solidification. Think of candle wax, right? So you had your candle on, it burnt for a while, it melted the liquid. Okay, so melting is good there because the wax melted into a liquid. But if you blow out your candle and you let the wax harden, right? It turns back into a solid. You don't say that the wax froze, right? That's not something we would say. We would say the wax solidified. Okay. Now, while we're talking about it, let's talk about boiling versus condensation. Okay, so maybe up here, if you're at the boiling point, right, we say that like water would boil at its boiling point. But again, that's pretty unique to water, right? We would talk about water boiling. So if you're at the boiling point and you're going to take the liquid and turn it into a gas, we usually use the word vaporization. We vaporize it. And if you're going in the opposite direction, if you got a nice vapor and you're going to turn it back into a liquid, the opposite would be condensation. Kind of like if you're in a bathroom and you're having your shower and it's quite a hot shower and you find that afterwards your mirror is all steamed up. That's because the hot water from your shower was turned into a gas. So you had all this water vapor in your bathroom. And the minute it hits your mirror is cold and you get condensation. Okay? So we do label them slightly different. If you're adding energy, you would melt it and then you would vaporize it. If you're taking heat away, you're going to condense it and then you'll solidify it. Okay? But now this graph here does organize what's happening. I've got two areas where I have temperature changes. So both of these would use Q equals mc delta T. Q equals mc delta T. And I do have one area where the temperature is not going up or down. If the temperature is not changing, this is going to be a spot where I use Q equals N delta H bar. Okay, so now we know which formula we're going to use for each part of the graph. It also gives us a chance to find temperature changes, right? Because look, right here we have, this is a delta T. If I'm going to use this equation for the liquid only exists in this area right here. So if I'm going to have a temperature change for this area, it has to be a temperature change that goes with just the liquid. So when I do my delta T is only going to be for here. When I talk about the solid, right, and I use the formula Q equals mc delta T, again, I need a delta T, but I need the delta T for the solid. So again, this part of the graph goes away, and so I'm just looking at the delta T for this area here in the graph. The delta T's, they tend to be the thing that cause the most trouble. People have trouble figuring out what's my delta T for my each section of the graph. But if you have your graph drawn like this, you can see this is the liquid part, so this is the delta T for my liquid. This is the solid part, this is the delta T for my solid. Okay? Now, there is a chance that the first question on an assignment will be, please draw the heating and cooling curve, but don't actually do any calculations. Okay, the chances that you will have more than one of those is relatively low, because if we make you go to all this trouble to do the graph, it's not a whole lot more work to put in the numbers, calculate the Q's, add them together, and then find the total amount of heat required for the process. Okay, so that's what we're going to do in our next problem. Okay, so for this one here, you've got, it says, please draw and label a heating curve for 100 grams of ethanol, and I've given you the formula, at minus 200 that is heated all the way up to 100. Calculate the total amount of heat required. Now for this one here, I've given you a whole bunch of information. Now again, depending on your textbook or the assignment or who's asking you to do this, not all these values may be given. You may have to go look them up. Often the melting points and boiling points of things come in like a table, so you'd have to go look them up in a table. Same thing with the delta H's of fusion and vaporization, right? They would be in a table somewhere and you'd have to go look them up. So all of these numbers have to be given. It's just they're not always given as a nice little block, right? Often you have to go look in supplementary tables. Okay, so if we're going to draw ourselves a graph, let's draw a nice big graph. Okay, my y-axis is going to be my temperature. My x-axis down here is either going to be heat added or lost, or perhaps it's just time that's passing, something like that. Now, as I said before, do them exactly the same every single time. So for this graph, the first thing I need to figure out is what is my highest versus my lowest temperature. Like, what's my window that I'm looking at? So the problem tells me that I'm going to start at minus 200 and I'm going to go up to 100. Okay, so minus 200 degrees is my lowest temperature. So minus 200.0. And my highest temperature is going to be 100 degrees. Your second step is always to put your melting and boiling point in, but only if they exist in this window here. So I got a melting point at minus 114. Minus 114 degrees would be about here, so that one's good. And my boiling point is 78.38. So 78 degrees would be about here, right? Just under the 100. If the person giving you the question wants you to have a scale, then you're stuck doing a scale and everything will be exactly where it should be. If you don't have to do a scale, personally, I like to spread things out. So if I have to include both a melting point and a boiling point, I'm just going to break it up into 3 sections. Okay? You can put in the scale or not, depends on the person giving you the problem and what they require. Now, let's write in my boiling point. Boiling point is 78.37 degrees. My melting point is a minus 114.0 degrees. Perfect. Now, we had said that at melting points and boiling points, the temperature doesn't change, so it's not going up or down. This gives me my horizontal parts of my graph. Now, if I look at the problem kind of as a whole, I'm starting at a low temperature and I'm going to a high temperature. So I'm going to heat and then flattens off when I melt. It's going to go up as I warm up the liquid, and then it's going to flatten as I vaporize. Then it's going to go up as I warm up the steam. So if we talk about horizontal sections, I'm thinking a horizontal section here and a horizontal section here. Okay? So your boiling points and melting points always have horizontal pieces. To link them together, they're always connected by these sloped sections. So slope, slope, and slope. Because you are going to warm up the solid ethanol, then you're going to melt it. Then you're going to warm up the liquid ethanol, then you're going to boil it, and then you're going to warm up the vapor. So let's label. In this problem here, you're actually applying heat. Okay, so if you apply heat to a solid at the melting point, then you will actually do some melting. So this is melting. If you apply heat to a liquid, you are going to vaporize. Right? On the way down, it would be condensation and solidification, but if you're raising the temperature, it's melting versus vaporization. Okay. Now, if we label up solid, liquid, and gas, if you're under the melting point, this would be a solid. If you're above the melting point, you are a liquid. And if you are above the vaporization, then you are a gas. Let's put in our formulas. These sloped sections always represent a change in temperature, right? I've got a solid at minus 200, and I am warming it up until I get to a minus 114. For this part here, I have a liquid. The liquid's at minus 114, and I'm warming it up to 78. Right? For the sloped parts, you are always changing the temperature. For the sloped portions, you're always going to do Q equals mc delta T, Q equals mc delta T, Q equals mc delta T. For these nice horizontal pieces where the temperature doesn't change, well, you have a formula for that, right? The formula for not changing, Q equals N delta H bar, right? That's for not changing the temperature. You are changing the phase, right? You're going from a nice solid to a liquid, but you are not changing the temperature. So I'll use this formula here. And I'll just kind of move this one over here. Q equals N delta H bar. Now, part of the reason why I like to make my graph so big is because I'm going to do each one of these calculations right where I've written them. Right? If I'm going to calculate the heat that goes with a solid, I'm going to calculate it right next to the solid. If I'm going to calculate the amount of heat that goes with the liquid, I'm going to calculate it right next to the liquid. If I'm going to calculate the amount of heat that goes with melting, then I'm going to calculate it right here. Okay, now there are a couple of back calculations that we need to do. If we're going to find our delta T's, then you need to be able to find the changes in the temperatures. Okay, so I'm going to be doing some delta T's right here. So let's say we want to talk about the gas first. Well, no, let's start at the bottom. So if we're starting at the bottom, here's your solid. This is your change in temperature for your solid. So the temperature is going to go from here, this is my initial temperature, to the melting point. This would be my final temperature. So you're going to go from initial to final. Okay, that's where you're going. So if I want to find my delta T, maybe we'll squeeze it in like right here. So delta T is T final minus T initial. My final temperature is a minus 114.0 degrees Celsius, minus my initial, which would be a minus 200 degrees Celsius, 0.0 degrees Celsius. Now, you do have a negative, but that's okay. That'll give you a positive. So I've got 114 negative plus a 200 gives me 86. So that is an 86.0 degree change. Now, am I happy with the 86? Yes, because the temperature did go up. Because the temperature is going up, that does give me a nice positive temperature. Okay, let's talk about the next section. So if I'm going to talk about this section here and I want to calculate delta T, the issue I have is that my initial and final change, right? If I'm talking about the liquid section is here. The liquid section starts here, so this is T initial, and it ends here, so that's T final, right? What used to be my final temperature for my solid is my initial temperature for my liquid, because that's what melting happens, right? You raise the temperature up, the last temperature that you had as a solid, that's the temperature you start at as a liquid, and then it comes back up again. Right? So that's why this graph is so powerful. It allows you to keep track of your temperatures. Okay, so let's say that we'll squeeze in this temperature change here. Okay, so delta T is T final minus T initial. So my final temperature is 78.37. Subtract off the negative 114. And so we pull out our calculator. 78.37 minus a minus is a plus, so 114 gives me 192.37 degrees Celsius. And again, I'm pretty pleased with this because the temperature is going up, so it's a nice positive delta T. All right, if we talk about the gas, at this point you can anticipate what's going to happen, right? If this is my gas, and this is the temperature change for the gas, and the temperature is going up, this is my initial, and this is my final. So for this part of the graph here, the last temperature of the liquid, T final for the liquid, becomes the initial temperature for the gas, because it's changing from liquid to gas. All right, let's squeeze in my delta T right here. So delta T is T final minus T initial. So my delta T would be final temperature of 100 minus the initial temperature of 78.37. So my delta T would be 100 minus 78.37 gives me 2163. So 21.63 degrees Celsius. And again, I'm pretty pleased with that, right? It's a positive number, temperature is going up, so I'm good. If this had been a cooling curve, so you had been coming downwards instead of going upwards, cooling curves would have given you negative delta T's for all three, right? Because you would have been losing temperature. You would have been dropping. Okay, so on the way up, they're all positives. On the way down, they're all negatives. Now, you can see that this thing gets pretty crowded pretty quickly. Okay, if you're doing it in pencil or pen, right, your numbers will be a little more compact than mine, right? This does tend to give quite large numbers. But if you make the graph the size of the full page, then you will have enough space here to do your delta T's, and you'll have enough space over here to do the rest of your calculations, right? It's very important that you keep things organized because it's very easy to lose things. Now, if we do talk about significant figures while we're at it, in the world of subtraction, sig figs are all about the least number of decimal places, right? For this one, I had 1 decimal place and 1 decimal place, so my answer should have 1 decimal place. For this one here, though, this has 2 decimal places, this has 1. So really, my answer should only have 1 decimal place. And the same thing here, right? 100.0 has 1 decimal place, 78.37 has 2 decimal places, so my answer really should only have 21.6. Okay? Now, if significant figures are not required of you, then I would probably leave it as 2163 and not round it off. But if you are required to do your significant figures, they should all round to just 1 decimal place. Okay, the other thing that I would like to do as sort of a getting ready for the calculation is to talk about the number of moles, right? For this formula here, the mass was given, the specific heat capacity was given, and now I have just found the delta T's, right? I have everything I need for MC delta T. I know the masses, I know the specific heat capacities, and now I know all the delta T's. So for these three, I am ready to go. For the other formula though, Q equals N delta H, for this formula, I'm not quite as ready. Right, I have my delta H's, but I don't have my number of moles, right? I've got a mass. So usually, if I didn't have this problem written here, I would take a small amount of space up in the corner, and that's where I would calculate my number of moles. Okay, so maybe I'll do that right here on this page. So the last thing that I need to do to get set up for this is to calculate my number of moles of my ethanol. Now, we do have a nice formula for that. Number of moles equals your mass divided by your molar mass. So for this problem here, they just give me the mass. They tell me I have 100 grams. Now the molar mass is going to come from your periodic table, right? When you look at your periodic table, each element has a molar mass given with it. So if we talk about ethanol, now, I've written it here the way an organic chemist would write it, showing you all the pieces. But if you're going to do molar mass, just kind of group up what you've got. You've got 2 carbons, so that's 2 times the mass of a carbon. You've got 3 plus 2 plus 1 is 6 hydrogens, so you got 6 hydrogens. And you've got 1 oxygen, right? So when we talk molar mass, I would like to know what's the total mass of this collection of atoms. So if you look it up on your periodic table, a carbon weighs 12.01. Your hydrogens each weigh 1.01. And your 1 oxygen weighs 16. Okay, so if I put that in my calculator, 2 times 12.01 plus 6 times 1.01 plus 16. Gives me 46.08, and the units for molar mass is grams per mole. So that would be 46.08 grams per mole. So if we do the division, 100 divided by 46.08, that gives me 2.170138889. Alrighty, so if you don't have to do sig figs, please don't write out all those, right? Cut it off somewhere so that way it's a bit more of a easy to deal with number. But if you are doing significant figures, in the world of division, it's all about the least number of sig figs. So 100.0 has 4 sig figs, 1, 2, 3, 4. 46.08 has 4 sig figs, 1, 2, 3, 4. And therefore my answer should have 4 significant figures. So I'll keep the 2, keep the 1, keep the 7, keep the 0, and get rid of everything else. Now the first number that I'm getting rid of is less than 5, so I don't need to round up. So my number of moles would be 2.170. And grams cancels, leaves me with just moles, which is kind of expected, right? If you're looking for moles, it has units of moles. Now I have everything I need to do the calculation Q equals N delta H, because the delta H's are given, and the N, I just calculated. Right, so maybe what I should do, because my graph is becoming a little bit full, is perhaps redraw my picture just quickly. Okay, so my lowest temperature was minus 200 degrees. My highest temperature was 100 degrees. We had a boiling point here of 78.37 degrees. I have a melting point here of minus 114 degrees. And my graph looks like this. Slope, horizontal, slope, horizontal, slope. Okay? Now, let's transfer in some of my information. I know that the delta T for this part of my graph, let's see if I can find it, 86 degrees. So this part here was 86.0 degrees. I know that my delta T for this part of the graph, and again, let's see if we can find it, 192.4. So 192.4. And I know that my delta T for this top part of the graph was 21.6. Okay, so what I've done is I've pulled out my delta T's from the 3 portions, and instead of having the calculations shown, I've just put them in. Now, if we do our labeling again, whoops, this was a solid, this was a liquid, this was a gas. This here was melting. This one was vaporization. And if we write in our formulas, this was a Q equals MC delta T. This was a Q equals MC delta T. This was a Q equals MC delta T. For vaporization, we got a Q equals N delta H bar. And for melting, we've got Q equals N delta H bar. Okay, so all I've done is take all of my formulas and re-pull them out. And let's pull out my moles. So I know that my moles would be 2.170 moles. All right, so what I've got now is the same graph. I've just given myself a little bit more space, probably not as much as I should have. I probably should have put it in the entire page. And the trick now is just to work my way through the numbers. So you could do formula, 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 formula in the order that they appear, right? Because you're you're warming the solid, then you're melting, then you're warming the liquid, then you're vaporizing, then you're warming the gas. Personally, I don't like switching back and forth between formulas. I find it too confusing. So I'm going to pick a formula and I'm going to work with it. So I'm going to do the MC delta T 3 times. So if we talk about our melting, Q equals the mass. The problem tells us that we have 100 grams of the sample, so 100.0 grams. Now, I need the specific heat capacity. The specific heat capacity goes with the solid. Again, this is why I like doing it right here, because it's a reminder. It tells me that when I go looking for specific heat capacity, make sure that it's the one that goes with the solid. So when I look at my list, I've got specific heat capacity of solid, liquid, and gas. I've got all 3, right? So I need to choose the right one. For the solid, it's 2.42 joules per grams degrees Celsius. So 2.42 joules per gram degrees Celsius. And the delta T for this part of the graph is right next to that part of the graph, right? The graph keeps me from getting mixed up. So it's 86.0. There we go, 86.0. Now if we pull out our calculator, it's just a multiplication, right? I've got 100 grams times 2.42 joules per gram degree Celsius times 86.0. That gives me, ooh, that's a big number. I should probably try that again. 100 times 2.42 times 86. It is a big number. Okay. Sometimes when I get big numbers like that, I'm afraid I made a calculation error. I put my decimal place in the wrong place, so I do like to check. Now, if we talk units, I've got a grams in the numerator and I've got a grams in the denominator, right? It's per gram, so grams and grams cancel. I've got a degree Celsius in the denominator and I got a degree Celsius in the numerator, so they cancel. So really the only unit left is the joules. So this is in joules, which is to be expected, right? We know it's a heat. We know heat likes to be in joules or kilojoules or calories or kilocalories. And since this had joules, then we have to be consistent. Okay, so that is my joules. Maybe I should put a little box around it because there's a lot of stuff going on here and I don't want to lose it. Now for this problem, it's just repeat, 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 right? If I want to do now for the liquid, it's the same mass. If you started off with 100 grams of solid ethanol, you're going to continue with 100 grams of liquid ethanol, right? It just liquefies. So this is still 100. Now the specific heat capacity here is for the liquid. That's why I have it in the liquid section of the graph. So if I come up and look for my liquid, I can see that its specific heat capacity is 2.44. And if I'm going to do the temperature change, again, it's right in this section. If this is the part of the graph I'm concerned with, then this is the temperature change for that part of the graph. So it will be 192.4. All right, so again, we pull out our trusty calculator. 100 times 2.44 times 192.4. And that gives me 46,945.6 joules. Now you will notice that because of space constraints, I didn't write in 100 grams or 2.44 joules grams degrees Celsius or the 192 degrees Celsius, right? I just left off the units. If you're required to do that, then you should probably put it in. But if not, because these three calculations are just so repetitive, I know that if this one is in joules, then this one's going to be in joules and this one's going to be in joules, right? They're very, very consistent. Okay, so let's do this last one. If you had 100 grams of solid, then you get 100 grams of liquid and you'll get 100 grams of vapor. Now that's often a little hard to picture because we think of like vapor, steams and things as being very, very light, but they do have a mass. It's just they take up so much space. But this would also be 100 grams. Now the specific heat capacity for this section would have to be the gas one, so it'll be 1.7. And the temperature change for this part of the graph was calculated for this part of the graph, right? Everything here is visually lined up to help you keep track of your numbers. So this would be 21.6. So my Q for that part of the graph is 100 times 1.7 times 21.6. That gives me 3,672. And again, I left out my units, but I know that these three are all the same calculations, so this will be in joules. And once again, I should probably put a box around this one so I don't lose it. And I should put a box around that one so I don't lose it either. Okay, so now I know the amount of heat required to warm up the solid. I know the amount of heat required to warm up the liquid. I know the amount of heat required to warm up the vapor. The only thing I have left to do now is figure out how much heat is required to melt it, how much heat is required to vaporize it. Okay, so let's move on to our other calculation. The Q here is the amount of heat for melting. The N is the number of moles, which we calculated a minute ago. So I can say Q equals 2.170 moles times. Now, the delta H's are going to be labeled according to where they come from. This delta H goes with vaporization, so you can see it's delta H of vaporization. In the world of chemistry, we don't like to use the word melting. Remember how we didn't like to use the word freezing? We preferred solidification. We also didn't like the word boiling. We liked vaporization. When it comes to melting, we like to use the word fusion. Now, all the rest kind of makes sense, right? When you talk about boiling and vaporization, you're familiar with both words. When you talk about solidification versus freezing, you're familiar with both and you can see the connection, right? Fusion is not a word that we use a whole lot outside of chemistry, okay? So if you're melting it, it's called fusion. So the delta H that I have to use is the delta H of fusion. So for this one here, it is 4.9 kilojoules. Kilojoules per mole. And sorry about everything getting crushed together, but that's why I was saying you want to put them as far, like as big a graph as you can, because there's a lot going on. So if I look at this, I'm going to have the 2.170 moles times the 4.9 kilojoules per mole. I've got moles in the numerator and I got per moles in the denominator. So they'll cancel and it'll leave me with just units of kilojoules. So when I multiply these two together, I will get it in kilojoules. Okay, so if I take my 2.170 times it by 4.9, I get 10.633. Okay, now I don't have room here, so I'm just going to squeeze it in on the top. So Q is going to be 10.633 kilojoules, right? The original number was in kilojoules, so that's in kilojoules. And let's put a little blue box around it so that way we can find it. This is the amount of heat required to melt the solid into a liquid. All right, now you've done one. Let's do the second one. So Q equals, okay, I did move it up again because I kind of ran out of space. The number of moles, so you still have the same number of moles, 2.170 moles. Now this delta H is for vaporization. So if your delta H is for vaporization, you just look up the right number, 38.56 kilojoules per mole. Once again, moles in the numerator and moles in the denominator cancel, and that leaves you with just kilojoules. And this is a beautiful calculation, right? It's just a multiplication. So 2.170 times 38.56 gives me a Q value of 83.6752 kilojoules. And let's put a little blue box around it. Excellent. So this is the amount of heat required to vaporize. Now I know it's all kind of crushed together, but the heat energy required to warm the solid, the heat energy required to melt the solid, the heat energy required to warm the liquid, the heat energy required to boil the liquid, and then the heat energy required to warm the vapor. Right? So you have them all, you just need to add them up. Now there is one slight issue. The formula Q equals N delta H, 99% of the time it'll give you your answer in kilojoules. Okay, because when we give you delta H's, here they are, we love giving them to you in kilojoules per mole. That's what we like. But when you do the Q equals MC delta T, 99% of the times these will be in joules, because we like to give these three numbers in joules, grams, degrees Celsius. So for this problem here, you're going to end up with some numbers in kilojoules and some numbers in joules. And you can't add them unless they're the same. Okay, so let's turn them all into kilojoules. Okay, we'll leave these two alone, but we will change these three. So if I want to turn joules into kilojoules, I divide by 1,000. So if I divide this by 1,000, I get 3.672 kilojoules. If I divide this by 1,000, I get 46.9456 kilojoules. And if I divide this by 1,000, I get 20.812 kilojoules. Now they're all in kilojoules, so now you're good to go. If you are worried about significant figures, I did purposefully leave it to this point because it's much easier to round these off to the right number of significant figures when they're in kilojoules. Okay? So if we rewrite them first and then we'll do the rounding. So to find my Q total, I need to add up all 5 of them. So if I take a look at this one as my first one, 20.812 kilojoules. It came from this formula here. The 100.0 has 4 sig figs, the 2.42 has 3 sig figs, and the 86.0 has 3 sig figs. So this answer should only have 3 sig figs. The 2, the 0, the 8, get rid of the rest. Because of what I'm getting rid of is less than 5, this would just be 20.8 kilojoules. All right. Let's talk about my melting fusing next. I'm going to work my way up my graph. So if I talk about the melting fusing, this was 10.633 kilojoules. But if we talk significant figures, this had 4 significant figures. This had 2. Only 2. Wow, that's not a lot. So my answer should have only had 2. I need to round it off at just 2, the 1 and the 0. But because the 6 is bigger than 5, I have to round up. So this would be 11 kilojoules. Okay, let's do the next part of our graph. In this part of my graph, I got an answer of 46.9456 kilojoules. If you look at your calculation, the 100.0 had 4, the 2.44 had 3, and the 192.4 had 4. So 4, 3, and 4. So my answer should only have 3, the least number. So 46.9, cut it off there. 1, 2, 3. Because the 4 is less than 5, I don't need to round up. So this would be 46.9 kilojoules. All right. Next part of my graph is the vaporization. So the vaporization, and again, ran out of space, so I'll write it up here, was 83.6752 kilojoules. This has 4 sig figs, 4 sig figs, so this should have 4 significant figures. So keep the 8, keep the 3, keep the 6, keep the 7, chop it off. Because the first number that you're getting rid of is 5, you are going to round up. So this will be 83.68 kilojoules. And my last piece of the graph, the warming up of the vapor. So when I calculated this, I got 3.672 kilojoules. So if I look at my numbers, 100.0 has 4 sig figs, 1.70 has 3, and 21.6 has 3. So the least number between 4, 3, and 3 is 3. So keep the 3, keep the 6, keep the 7, get rid of the rest. So this would be 3.67 kilojoules. Okay, that's the 5 heats that go with this. If I want the total, I just need to add them up. So let's add up these down here. 20.8 plus 11 plus 46.9 plus 83.68 plus 3.67 gives me 166.05 kilojoules. So the total amount of energy required to take a block of really cold frozen ethanol and heat it all the way up to really hot ethanol vapor is 166.05 kilojoules. Again, if you want significant figures, when you're adding, it's all about the least number of decimal places. So 1 decimal place, no decimal places, 1 decimal place, 2 decimal places, and 2 decimal places. So the least number is none. So this would round to just 166 kilojoules. Like I say, the problem is not a hard problem, but there's a lot of pieces to it. Like this particular one here, you had 3 different heatings and you had 2 different phase changes. So there was quite a bit of like a lot of givens, and there's 5 separate calculations. Right, if I had drawn my graph a bit bigger and if I had used like a pen or a pencil to write smaller, I would have been able to put the calculations in and have a bit more space to see what I was doing. Right, organization here is the key. Now the other thing that I wanted to say is if we go back to the diagram here, this picture didn't have 5 calculations, right? If I was going to do this one, it would only have 1, 2, 3 calculations. So for a lot of these problems, you don't actually end up having to do all 5, right? You would end up doing just 3 or perhaps 2. Okay, so they're not all going to be gigantic. The other thing that I wanted to point out, if you are cooling, your delta T is going to be a negative, which means this Q is going to be a negative, right? Your delta T is a negative, so your Q is a negative. If you're talking about solidification or condensation, which is the opposite, in the world of thermodynamics, the opposite process always gets the opposite sign. So over here, if we go back to this problem back this way, when I gave the delta H of fusion and vaporization, here, they were both positive numbers. But if I wanted to call this, instead of fusion, I wanted to call it solidification, it just becomes a negative 4.9. Right? When I talked about the delta H of vaporization, if I wanted to talk about the delta H of condensation, this would just become a negative number. Okay? So when you do this back here, if you were solidifying, this delta H would have been a negative, and so your heat would be a negative. In these problems, if it's a heating curve, every single heat will be positive. If it's a cooling curve, every single heat will be negative. In these problems, you'll never have a mixture. There will never be a spot where you have both positive heats and negative heats. They're either all positives or they're all negatives. Okay, so I hope this helped. These problems are quite large, but if you think of them as just a series of steps, then they're not quite as complicated. As always, thank you for joining us here at Chemistry with Dr. Clark.